So let us have an example depicting the logistic function. And in this example, we are going to compare two different functions, but with seemingly similar characteristics. So our first function is an exponential function. This is f of x is equal to 2 raised to x. So this is an exponential function. And our second example is a logistic function. Which is modeled by 2 raised to x over 2x plus 1. Now let's set this ahead. Okay. Now let us compare the values by first defining their characteristics at certain values for x. Now at the small values of x, they have their own characteristics, right? So they have their own characteristics. And what do I mean by small values of x? When I say small values of x, these are domains or x values such that the values are small, like in the case of -2 to 2. What else? Maybe we can still put -10 up to 10. That's still acceptable. But now, let's say we move to a case wherein x is positive and x is large. So let's say this notation is means it is very large. Okay, so x is very large. And let's take an example at x is equal to 100. Well, 100 is not commonly used in algebra, especially when graphing is concerned, because it is very big, such that it will cover an entire page, or maybe a page with a math page with grid lines couldn't even fit. So x is equal to 100 could be considered very large. Now at this value, let us see the behavior of our g of x. So our g of x, or let's put it like g of 100 now. So g of 100, our x is 100. And this will give me 2 raised to 100 over 2 raised to 100 plus 1. And taking your calculator with you, when you try to calculate it, so let us calculate together. 2 raised to 100 divided by 2 raised to 100 plus 1, this will give me 1. Why is that so? Now, at very large numbers of x, large positive, okay? Positive values of x, g of x levels off to 1. It levels off to 1, okay? To the value 1. Okay. Now, why is that so? Your 1 compared to this is very, very small, such that it is negligible. 2 raised to 100 is actually 1.2676506 times 10 to the 30. Look at that value. 1.2676506 times 10 to the 30. And 1 compares to this one is very negligible. That's why it's almost nothing. So 2 raised to 100 divided by 2 raised to 100 plus 1 levels off to 1. So that's the behavior of your g of x at very large positive values of x. Okay? Now let us say, let's take the reverse. Okay? Now for very large, say it like this, at very large values of x, but now it's negative. So at x less than 0 and x is very large. Okay, let's take again the x is equal to negative 100 as an example. Or let's get it as a premise. Then your g of negative 100 will be equal to 2 raised to negative 100 over 2 raised to negative 100 plus 1. Okay? Let's see if we are actually doing the right thing. Yes, we do. So a very large number of negative x, this will give you 2 raised to negative 100 over 2 raised to negative 100 plus 1. But again, compare this number here. 2 raised to negative 100 is actually 2 raised to negative 100. This gives me 7.8886 times 10 to the negative 31. Now compared to 1 now, this value here is very negligible such that it's taken to be 0. Okay? So now we will have 2 negative 100 over 1. And thus will behave like 2 negative 100, or in this case, our g of x will tend to behave like 2 raised to x. Do you get the idea? At very large positive numbers for x, your g of x levels off to 1. But for very large negative values of x, your g of x tends to behave like your f of x. So it tends to behave like an exponential function on large numbers or large values of x when x is less than 0. Okay? So which confirms to the standard to our illustration for very large numbers of negative x. So it's here, it tends to be an exponential function. And for very large numbers of x, let's say here, it levels off to a certain period or a certain y value. Now in that case, that is 1. Okay? Now we want to express our g of x, the exponent or the function g of x, the one that we use here. So let's write it here. G of x is equal to 2 raised to x over 2 raised to x plus 1. Now we want to transform this function into an expression or into a function wherein there is only one exponential function. So what we are going to do is to multiply both the numerator and the denominator by what are we going to do? We are going to multiply both by 2 raised to negative x. Remember that 2 raised to negative x is still an exponential function. Okay? So let us multiply by both numerator and denominator by 2 raised to negative x. So this one will have 2x minus x, and then this will be 2x minus x plus 2 raised to negative x. We're going to use the distributive property for this portion. So now this will give us 2x minus x is 2 raised to 0 over 2 raised to 0 plus 2 negative x. So this will give us 1 over, because anything raised to 0, any variable, any number raised to 0 is always 1. So this will be 1, this will be 1, and we will have 1 over 1 plus 2 raised to x. So this is our answer. Okay? So we are successful in transforming the equation g of x is equal to 2x plus 1 into this function. This expression. Okay? So we go now to the definition of a logistic function with its general equation. The definition states that f of x is equal to a certain constant, c, over 1 plus ae negative bx or f of x is equal to c over 1 plus a b negative x. Notice that we have two different bases. Okay, let me write them again because they seem not so clear. So f of x is equal to c over 1 plus ae negative bx, and the other one is f of x is equal to c over 1 plus ab negative x. Notice that we have two different types of bases. The first base is e. So the base of the first function f of x is e, and the base of the second function is b. Okay? So a, b, and c are constants, and the domain is all real numbers. As illustrated here, your domain would be from negative infinity to positive infinity. So all real numbers are included. So in this case, let us take a note, a special note at when your base is e. Okay? Now, when your base is e, okay, as x decreases or becomes more negative, e raised to negative x becomes larger. Now let us see that. Let's say our x is negative 20. So at x is negative 20, and let's say my b is, or my a is 2, my b is 3, and my c is any constant 5, let us say. So having my calculator with me, I could actually get the value of my f of x. So my c is 5 divided by 1 plus a is 2 times the e. Where is the e? Shift ln, so that's e, negative, my b is 3 and my x is negative 20. So notice that as my x becomes more negative, My answer here would be 2 points okay, so negative. My e raised to negative x becomes larger because look at this is negative, right? So multiplying this by a negative number, so negative 3 times negative 20 is equal to e raised to 60, and e raised to 60 is just 1.14 times 10 to the 26. So it becomes larger, okay? And when my x is more positive, my e raised to negative x becomes smaller. So which makes sense, because if my x is 20, so that will just give me e raised to negative 3 times 20. So that gives me e raised to 60, negative 60, or 1 over e raised to 60. And 1 over e raised to 60 becomes in this case 8.76 times 10 to the negative 27. So look at the difference. Okay? So this is the definition of the logistic function and the general equation of the logistic function.